Okay, so for this video, we'll be looking at success criteria C. So please check that you have watched the video on success criteria A and B for work, energy, power, right, before you watch this video. So success criteria C basically is to state the principle of conservation of energy, and then you apply this principle to new situations or to solve related problems. So I will say that this concept is pretty important for this chapter. Now, what is the principle of conservation of energy? It states that energy cannot be created or destroyed, right? We cannot create energy, we also cannot create energy. However, it can only be transferred from one store to another, right? So, example, energy in the kinetic store can be transferred to gravitational potential store, things like that. Okay, so the keyword here is transferred from one store to another. The second part of this is that the total energy of an isolated system is constant. So this is actually a definition, so you need to memorize this. Alright. So to illustrate the principle of conservation of energy, we can use an ideal pendulum. The meaning of ideal means that it will continue swinging in the absence of air resistance. Alright. But we know that this is not actually possible in real life. But first, we use an ideal pendulum to illustrate our point. So, at first, we will move the pendulum up from its rest position from B to A. So, when we raise it, it is at a height of x above the horizontal surface, horizontal level. And at position A, there is energy in the gravitational potential store. Okay? Because this is the maximum height that we bring it up. Of course, we can bring it higher, but for now, we just bring it at a height of x above the horizontal level. When we bring it up, we hold it there, it is not moving. So over here at A, there is energy in the gravitational potential store. Okay, so the GPE is max, but because we hold it there, it's not moving, the energy in the kinetic store is 0. Now, when the pendulum is released, it will swing downwards. Okay, when it reaches B, the velocity is actually maximum. That means the kinetic energy is actually at a maximum. And because it has reached the lowest point, we choose this horizontal level as the reference height, right? It has reached this level. So, the energy in the gravitational potential store becomes 0. And since it's ideal, it will swing back up to C, okay, with the same height of x. That means now at C, the height is maximum, so the gravitational potential energy is maximum. However, when it reaches the maximum height, okay, this is important, the speed is 0. Why is the speed 0? Because if the speed is not 0, it will move higher, isn't it? The reason why it didn't move higher was because it has already reached maximum height. Therefore, if the speed is 0, the energy in the kinetic store will be 0. So basically from A to B to C, okay, we have initial energy of gravitational potential energy, right? So we fix it at 5 units. Then when it moves to B, so this is at A, when it moves to B, we see that it transfer 5 units of its energy in the gravitational potential store into the kinetic store. Okay? Because it is now moving at maximum speed. Then this is still at B, okay, and as it moves to C, it transfers 5 units of energy in the kinetic store to 5 units of energy in the gravitational potential store. So if this continues, then C to B to A to B to C, these 5 units of energy will be transferred from gravitational potential store to kinetic store and back to gravitational potential store again. Okay, in this case, the ideal pendulum will just keep on swinging forever. But in the real world, when there's presence of air resistance, right, air resistance will sort of be a force that opposes motion. Some of this energy, okay, will be transferred mechanically, okay, to the internal stores of the pendulum bob and the surrounding. Okay, so initially, let's say I have 10 joules of energy in the gravitational potential store. Okay, 10 joules. 2 joules will be transferred to the internal store of the pendulum, because the pendulum, when it swings against air, it will heat up. Okay, and this heat energy will be transferred to the surrounding by wave, by propagation of wave. Where did the 8 joules go to? It will be transferred to the kinetic store, okay, at B. Then remember, at B, it will swing to C, okay, and we still have 2 joules of energy that is transferred to the surrounding, and therefore we will have 6 joules left, or 6 joules to be transferred to the gravitational potential energy at gravitational potential store at C. Okay, maybe I'll draw it here. So this is A. I have 10 joules of energy in a gravitational potential store. Then as it swings to B, 2 joules will be transferred to internal, to the energy in the internal store and the surrounding. Okay, internal store of the pendulum, and surrounding. Okay, that means I have 10 minus 2 joules. I have 8 joules transferred to the kinetic energy store. Okay, then this is at point B. It will continue swinging to point C. So similarly, I will also have, assuming the same 2 joules transferred to the internal store of pendulum and the surrounding. Therefore, at C, I will now have 8 minus 2 joules. I'm left with 6 joules of energy in the gravitational potential store. So if it does come back, and of course it does, it will still lose another or transfer another 2 joules. So now I'll be left with 6 minus 2, so equals to 4 joules of kinetic energy, or energy in a kinetic store. So you'll find that the energy will actually be transferred to the surrounding and also to the internal store of the pendulum. And as a result, the energy that's being transferred to the kinetic store or to the gravitational potential store will get lesser and lesser, and eventually this real life pendulum, or this pendulum in the real world, will stop. Okay, so it will eventually come to a stop. But if we were to consider the pendulum and the surrounding as a whole system, right, the total amount of energy in the energy store of the pendulum and the surrounding remains constant. That means eventually it will still be at 10 joules. Okay, so this is the principle of conservation of energy. So now let's solve this question. All right. I think if you were to apply principle of conservation of energy, you should be able to solve this question. So maybe you can pause the video now. Okay, and then after you work out the answer, you check the video again for the correct, to see if your answers are correct. Okay, I hope you have taken some time to try out this question before watching the solution. Alright, so for C1, the figure below shows a simple pendulum. Okay, it's not an ideal pendulum. It swings from A to B to C. So it goes from A to B to C. The pendulum bob has a mass of 20 grams. So when you're doing this, you should annotate the mass is 20 grams. But because remember, this is a SI unit chapter, so everything has to be in SI unit. So I need to convert my 20 grams by dividing it by 1000 to get 0.02 kg. Okay, this is important. And we see that from A to B, there is a height difference of 15 cm. And again, this is a SI unit chapter, so I need to convert this to meters. So I'll get 0.15 meters. Okay, so you should always check the units and do some background work before we start. Now, the bob is released from position A. That means initially, the speed is 0. Okay, so if it's released, now it is at a height of 15 cm above B, right? So we take the height of B, or we take this horizontal level as the reference point. So the energy at A, because the speed is 0, so energy in the kinetic store is 0. But because it's at a height above B, there's going to be energy in the gravitational potential store. Okay, so maybe for this I should write as EK, because previously in the video I told you EK, the formula is half mv square, right? So let's stick to that. And this is I'm going to calculate energy in the gravitational potential store, so I should write as EP. So it's equals to mgh. Okay, so the bob is released from position A. Calculate the change in energy in the gravitational potential store. So this is actually my EP of the bob when it swings from A to B. So at A, the EP is found by using mgh. So if you have done your conversion, it becomes very simple. So we get this. So I get 0.030 joules. Remember to leave your answer in either 2 or 3 SF. Now state the energy in the kinetic store of the bob at position B. So we assume that all energy in gravitational potential store is transferred to kinetic store. Okay, so this is the assumption. So the energy in the kinetic store will then be equals to 0.030 joules. Now calculate the speed of the bob as it passes position B. So at B, it actually only has energy in the kinetic store. Okay, so it's equal to 0.030 joules. And because it is at the lowest height, at the reference line, so the energy in the gravitational potential store is 0 joules. Okay, so since we have EK, which is the energy in the kinetic store, and EK is equals to half mv square, we can calculate what is the velocity. So we fill in all this, 0.02, okay, and v square. Take note that the square belongs to v. So I'll get 0.3 square root, sorry, it should be 3. Okay, so square root 3 equals to v. That means my v is 1.73 3SF. The units is meter per second, right? Remember, everything should be in SI unit. So this is answer for C. Now D, when the bob swing up towards C, it reaches a maximum height that is lower than position A. Why is that so? Explain why the bob is unable to reach the same height as position A. Okay, so because this is not an ideal pendulum, there's going to be air resistance. So as the pendulum bob swings from B to C, it experiences air resistance. Okay, air resistance, and has to do work. You have learned in your lower sec science that you have to do work against the air resistance, right? So some energy has been transferred to internal energy and also sound energy of surrounding, right? So we have hence only some of the kinetic energy has been transferred to gravitational potential energy, right? So because it did not get the full transfer of energy from kinetic energy to the gravitational potential energy, so the height will be lower. Okay, please try C2 as well. Okay, so if you have not tried, please pause the video. Okay, so for C2, a ball rolls up a frictionless slope. That means there's no friction to come to a rest before it rolls down. So I'm going to draw a slope to show how it looks like. So it rolls up a frictionless slope, okay, and it comes to rest, right? So initially it was here, somebody give it a push, it rolls up, okay. Over here it comes to a stop, so the V is 0 meters per second before it rolls down. So which of the following graph shows the correct energy in the kinetic store and gravitational potential store of the ball during the upslope motion? So we are looking for the upslope motion. That means we don't care about this. Okay, so if it goes up, so in order for the ball to go up, the initial velocity must have a value equals a certain value, correct? So imagine you're down at a slope, you want to push this ball up, you need to push up with a certain force, and the ball will move with a certain initial value for its velocity. Then when it rolls up to the slope, the V or the final velocity becomes 0 before it then rolls down. So at the bottom, it has energy in the kinetic store to be maximum. EK is maximum. But at the bottom of the slope, the energy in the gravitational potential store is 0. But at the top, EK is 0 because the velocity is 0. It stopped momentarily, but EP is max. So you see that there's a transfer of energy from EK to EP, right? And the transfer, and initially the EK must be max. That means B is wrong because initially KE is 0, okay, as it moves up. That means D is wrong as well because initially KE is 0, but we determine that if the ball were to roll up, the velocity or initial speed must be of a certain value, then the EK cannot be 0. So it's either A or C, but which one is it? Okay, because both of them started at maximum value for the energy in the kinetic store. Alright, I would say that it's A and not C. Why? Because if I were to ask you to think about halfway, okay, there will be half of the energy in a kinetic store and half of the energy in the gravitational potential store, but they add up to one part. So half of the energy in a kinetic store will be transferred to the energy in the gravitational potential store. Okay, so it's a linear thing. The transfer is a linear thing. So answer is A. Okay, if you are not convinced, you can actually do some math calculation. Please look for me. Okay, so that was for success criteria C.